Hey everyone, in today's video we're going to look at calculating net forces. So first off, what is a net force? The word net literally just means total, and that's what net forces are. They're the total forces for a system. So we have all these free body diagrams. These are we drew these in the last video, and we're going to find the total forces in each of these diagrams. So for example, in the first diagram, we see there's 4 different forces, and we want to find the total overall force in the x direction and in the y direction so that we can predict how this object will move. Now, you'll notice that we're talking in the x and in the y. That's because we need to do things in separate directions because it makes calculation of stuff later much, much simpler. So this is really what net forces is all about. It's about doing questions with these net forces later. Because right now, we don't actually have any numbers here. We're not going to be calculating values. We're just going to be creating equations for the net forces that when we add values later will allow us to do more complicated calculations. That's all we need to worry about for today. For reference, the symbols we use for net forces are literally just Fnet. And we can do Fnet with an X or Fnet with a Y to indicate the net forces in a specific direction, which we'll be doing. Now, before I start net forces, there's a little kind of math concept we're going to review quickly because it relates to doing more complicated net forces, especially in example 3 here where we have an angle. You can see the angle here. And the concept we're going to review is called vector components. You might remember this from kinematics. It's pretty straightforward if I explain it well. We'll see. So I'm just going to draw a random coordinate grid, and we're just going to have a random vector here. So this is just a vector. It could be any vector. Doesn't really matter. The point I'm making here is let's call this vector d1. It's a distance. Now, the deal with this vector is that it has a direction. It actually has 2 directions because we usually say, that it's south and then a certain number of degrees north, or in this case, it's north and a certain number of degrees east. Because here's north, south, east, and west. And so we're north, and then we're a certain number of degrees east. And that's like theta degrees, and it doesn't really matter. The point is this is the vector. And if we were to write this vector, like I said, we'd be doing like some number of, let's say meters, and we'd be saying it's north some number of degrees east. And that's how we'd be doing this vector. However, when we need to do calculations with vectors, 2D vectors like this format becomes a little less useful. When we do calculations, the most convenient thing to do is usually to convert into vector components. And the way to convert into vector components is pretty simple. Let's imagine this vector is like a person who's walking from here at the origin to his house over here. So he's going for a walk to this building. Now, there's one way to get to that building is just along the path of this vector. He literally walks like this to the building, done. But there's a couple other ways to get to this building, and we're going to put a restriction on this person. He can only move in straight lines along horizontal or vertical axes. So he can only move, for instance, along this line or along this line. Given that, how can we get this guy to the house in the same way that this vector does? There's basically 2 possible ways. The first way, I'm going to draw this in red, is that he could go this way until he's in line with the house, and then he could go this way until he reaches the house. The second way is just to go this way until he's in line with the house, and then this way till he reaches the house. That's a 2-step process in both ways, so it will take longer, but crucially, the guy ends up at exactly the same place. These lines, I'm drawing the red ones, either these 2 here or these 2 here, are the vector components of D1. And because of the components, we call them D1x and D1y, obviously because this one's along the x-axis, the other one's along the y-axis, and we're able to find them. Now, how do we find them? Well, to do that, we really need to take out everything extraneous. So I'm literally going to redraw it without anything else. Here's D1. Here is D1x. You could have used the other set. I'm just using these. It doesn't really matter. Here's D1x, and here's D1y. Now, what does this look like? You might notice that it is a right triangle. There's a right angle here. Here's our triangle. And what we're going to do with this triangle is we are going to find x and y, or at least get formulas for them, because we don't have numbers here. So we are going to have two equations which start d1x equals and d1y equals. And the way we're going to use these is by using SOHCAHTOA, which we remember is trigonometry, and basically remembering that we probably know this angle. Even if we knew this angle, theta, over here, we could find this angle because it's just 90 minus theta. So we know this angle. So we know this angle, and we know one side because we're going to know what d1 is from the vector. So we're now going to find the components. And the way to do this is to notice that, okay, d1x is the adjacent side of this triangle. Remember SOHCAHTOA, this, relative to this angle, this is the hypotenuse, this is the adjacent, and this is the opposite side. So we notice that d1x is the adjacent side. So the variables involved here are d1, which is the hypotenuse, and d1x, which is the adjacent. And that is ka, or cosine. So d1x can equal d1 cosine of theta. And that's just taking the fact that that cosine of theta equals, it equals a over h, adjacent over hypotenuse, and then putting in d1x as a, and putting in d1 as h here, and then we can rearrange this in order to get this. The alternative for d1y is just going to be using the opposite in the hypotenuse, and that is sine. So we can say d1 sine of theta. And voila, we've arrived at two equations which will represent the two vector components. So that's how we find vector components, and it's pretty straightforward. We're going to need to use this in example 3 when we get there. So just keep this in mind, that these are how we deal with vector components. Okay, let's get back to the actual thing, which is calculating net forces. Net forces need to be calculated, and we're going to do that for the first diagram, which is right here. This is diagram 1. If we look at this, there's 4 different forces, but there are 2 forces x and 2 forces on the y, so we're going to deal with them separately. So let's take a look at these forces. We're going to need to be finding 2 values. We're going to need to be finding an F net x, which equals something, and an F net y, which equals something. So let's just look at F net x, and the first thing we need to do is assign a direction, and my personal preference, and probably what you want to do most of the time, is say that right and up are positive. But sometimes you might want to do something different, but for now we're going to say right and up are positive. So let's take a look at this. On the x, we have 2 forces. There's Fa, this active force, and there's Ff of k, the friction force. Let's start by just putting them here. With no operators, it's just Fa and Ffx. Ffk. So now, let's look at these and basically say, okay, is the first one going to be positive or negative? Well, it's going to be positive because it's going toward the right, which we just said over here is the positive direction. Ffk is going to be negative. So, because it's going the opposite direction. So, we can put a positive here, which no one needs because it does nothing, and a negative here. That's it. We found the net forces in the x. That was really quite simple. The net forces is literally just going to be the active force, which goes one direction, minus the kinetic friction force, which is going the other direction. Let's take a look at the net forces on the y. Well, these are not much more complicated. We have the similar 2 forces. We have Fn, floor, which is going in the positive direction, so it's going to be positive, and again, I don't need to do that. And then there's negative, this force of gravity. And the force of gravity, I should actually do this with a little g, not a big G technically, is the negative one because it's going down rather than up, which we had said is positive. And these are the formulas for net forces. That was really quite simple, and that's really all there is to it. It just gets a little more complicated when we deal with more complicated diagrams. Speaking of which, example 2. Now we have A and B. B, you can probably see, is pretty simple. It's just on the y direction. So I'm actually going to disregard it, and we're just going to do A. And you'll see that A is pretty similar to what we just did for the previous example. But we need an F net x. And there are two forces on the x, again assuming up and this way are positive. There are two forces on the x, Ft, the tension force, and Ffk, the friction force. And so we can pretty just know that here we got the positive Ft because it's going right, and the negative Ffk, which is going left. Easy peasy. F net on the y, on the other hand, is going to be a positive Fn floor, and a negative F of g, gravitation. And that's already it. It's literally that simple. I told you things would get more complicated. This is why. We're going to take a look at this diagram. And the first thing you need to understand about this diagram is doing this is wrong. Why is it wrong? Because if we look at the actual thing that we drew a diagram of, which is this system, we'll notice that like the up direction of these boxes is not really straight up. Sorry about that. It's not really straight up like this. It's actually kind of going in a direction. Now we just did A, and it's kind of going this way. That's kind of up. And this is down from the box's perspective. If we were to draw compass directions here, we would say that we have like north over here, south over here, east over here, west over here, and east over here. Now you notice how that's been rotated from the normal way we do this, which is north straight up. And that's really important to understand because it explains why this becomes ever so slightly more complicated. So I'm just going to walk through it, and when we get to the complicated part, you'll see why. Let's start with the forces on the x. If we look on our east-west kind of axis, there's two forces, the tension force and the friction force. And this is very similar to last time. F net x is just going to equal the positive. This is wrong, by the way. It should be like this. It's going to equal the positive tension force and the negative kinetic friction force. F net y. Well, we're going to start out pretty simple here. The first thing we see that is on the y is this positive normal force. And then we get to an issue. Because the next force here is the force of gravity. But if you look at it, it's not pointing quote-unquote down. It's pointing what we're seeing as down, but it's not pointing south on the diagram. It's some angle away from the south. And that's going to be a problem when we are trying to actually look at it and figure out, what is this thing here? So this is where our knowledge of vector components is going to become very important. And that is because of what we're about to do, which is think about this diagram rotated on its side, and we're going to draw the vector components here. What are they? Well, one of them is going to be straight on the y-axis, so this direction, and one of them is going to be straight on the x-axis, so this direction. And if I was good at drawing, that would land at the same point here. Those are the vector components of FG. And we're literally going to write them as FGY and as FGX. And these vector components are now going to be used to calculate this. Why? Because FGY is now facing straight up on the y direction, so we can use that without fear. Here's FGY. And we now have an extra force, FGX, which is on the x direction, and it's negative. You can see it's pointing in the negative direction. And so we're going to need to add it here in the negative direction. So these are our slightly more complicated net forces. But this wasn't much work. The problem is if we wanted to actually do anything useful with these equations, we would have to know what FGX is, which we don't, and what FGY are. And the way to figure that out is our very handy formulas from over here when we were dealing with doing vector components. We're going to take a look at this and notice that if we're dealing with SOHCAHTOA, let's suppose we know an angle here, and we would need to replace these with the proper formulas. So we kind of have to look at, okay, what angle do we know? And this is where it gets a little tricky, because in most of these questions, the angle we would know is the angle I labeled as theta, which is not immediately helpful because we would need this angle. So we're going to use another fun trigonometry thing called similar triangles. And to do that, I'm literally going to draw this triangle the way you're probably seeing it right now, separate from this diagram. And it's going to look something like this. This is the blue triangle over here. I'm just drawing it over here. And then you'll notice that there's this line here, and we have an angle here. And we're like, okay, I need to figure out this angle, which I'm going to draw in blue. The way we're going to do this is by constructing another triangle, and this time the triangle is going to be over here. So on our diagram here, what I'm doing is essentially extending this line and filling in this kind of thing. And if we look at this triangle, we're like, okay, that doesn't really seem helpful to us. But it is helpful, and that's because there's a right angle here and a right angle here. And so these two triangles are what we would call similar triangles. And what similar triangles mean is that they have exactly the same angles. Now we could prove this, it's complicated, don't worry about it. The point is that they are similar triangles, which means that the angles of this triangle, that is this angle that we know here, and also this angle, map directly onto these angles here, the ones I'm about to mark in red, here and here. So the green angles go on to the red ones. And so, since we know one of the green angles and the other one's 90, we could then figure out either of the red angles. And when we do practical problems in a later video, you'll see how this actually gets applied in practice. But the point is, the similar triangles lets us figure out this angle here, this angle theta. And that's critical because once we know this angle theta, our fun formulas that we used before for vector components, namely the d1 cos x and d1 sin x, suddenly became perfectly useful because we can now replace fgx with the knowledge that it's actually fg, it's fg followed by the cos of theta, and we can replace fgy with the knowledge that it is the sine of theta. And if you look at that, I got those in the reverse order, but the point stands. So fgy is being replaced, being the opposite side, with the so part, which is sine, and fgx is being replaced with the ka part, because it's the adjacent, which is cos. And there we are. By using SOHCAHTOA on this triangle, we have now been able to create these two equations. That was very complicated. Hopefully I tried to make it as simple as I could. All of these things make a lot more sense when we put numbers into them and use them in practical problems, which we definitely will in a later video. So don't stress too much if you had very little clue what was going on here. Things will start to make sense. But at a wider view, what we've done here, we learned about vector components, and then we went and applied it here. Hopefully, at least examples 1 and 2 were pretty straightforward as to how we find vector components. But 3 is a little more complicated, but hopefully this made a bit of sense. If not, when we do practical applications of this, it'll start to make a lot more sense. I do promise that. But in general, that's it for finding net forces. These net forces become useful, again, when we do actual practical problems with numbers, which are coming up. For now, it's a matter of practicing finding formula from these free body diagrams, and that's what's really important here, so hopefully you pick that up. That's about it. Thank you for watching this video, and I'll see you next time.